In this video we will learn about a technique of panel data which is known as the fixed effects with Driscoll and Kraay standard errors approach. Right now we are looking at a publication in which we used this technique because there was a need for this technique, and this is the title of this paper. It is me and my co-author. So we had a panel data of 24 countries and we had a certain number of years, and we had to resort to the Driscoll and Kraay standard error method because of the problems with the fixed effects random model effect, as there were heteroscedasticity and autocorrelation in the results. So I'm going to go to that place where we have executed the results and the commands. This is the test for finding out if we need panel effects model or OLS model, and here we have Houseman test, which decides about which kind of the panel effects model is suitable, either fixed effects or random effects. So the results are following, and here we have this Breusch-Pagan Lagrangian multiplier test, which is statistically significant. So it means that there is a presence of panel effects, as the null hypothesis of no panel effects is rejected. So we have to choose between fixed and random effects model, and for that we have Houseman test, and in the Houseman test, if it is statistically significant, just like it is, it means that fixed effects model should be preferred. We have done this before in the previous video, that is the fixed and random effects model. These are the commands that we have used here, and now we see the results. These are the results of the fixed effects model primarily. This column, that is column 1, and we have the results here. These are the coefficients and these are the p-values, and this is the command that we used. Now we come to why we need the Driscoll and Kraay standard error method. For that we have to see if there is autocorrelation and heteroscedasticity, and this is where we have applied the tests. It means it shows that we have the presence of serial correlation or autocorrelation, and heteroscedasticity is also present. This is the description of the test that you can pause the video for and read. However, these are the results. Let us zoom in a little bit. This is the heteroscedasticity serial correlation test, and this is the test for heteroscedasticity. The null hypothesis is rejected of no first order serial correlation, so there is serial correlation in the given data. And then we have the modified Wall test. It is statistically significant and the null hypothesis is rejected, so there is not the same variance for all the I. It means that both autocorrelation and heteroscedasticity, they are evidenced, and we have to resort to some superior technique as compared to the fixed effects. Actually, this is a remedial measure for the fixed effects model when it has the problems of heteroscedasticity and multiclinarity. So these are the results of the Driscoll and Kraay standard error method, which is actually a version or the remedial measure for the fixed effects estimation. These are various variables, and this is the coefficient, and this is the value of R square, and so on. And these are the results. What you can see is that statistical significance of BBS, that is broadband, is kept. The statistical insignificance of foreign direct investment is also retained. So is the case of the tertiary enrollment rate. However, for population and for government expenditure, both of them are significant, so its statistical significance is retained, and trade openness is insignificant in both of the cases. So it means that Driscoll and Kraay standard error method has not upsetted the results. The results are similar. It has also a favorable effect on the R square, which is also a welcome thing. So this is how we can use the Driscoll and Kraay standard error method. Now we will go towards the execution of it on Stata. This is the command, and we are going to use it in the software Stata. So now we are in the Stata, and you can see I have loaded the file already, as these variables are already visible. This is similar sort of data, and we have the variables. So now let's start with the simple regression, and let us see. This is the random effects model, primarily because we wanted to calculate, estimate a few other variables and estimate the statistics. This is the xtscc, that is the Lagrangian multiplier test for random effects. It is actually for the decision between pooled OLS or panel effects model. So it is statistically significant. It means that we can go for the panel effects model, that is either the fixed effects model or random effects model. So we start with the fixed effects model. As you can see, these are the results, and the other command is to store these estimates so that we could compare it with the results of random effects model and choose between these two. So the results are stored, and now we go towards the random effects model, which is here. This is the command, and then finally the Houseman selection test, that how either of these would be preferred. This is that command. When we enter, the result is that it is statistically significant. So it means that it is a fixed effects model that can fit here. But here we cannot stop, because the problem of heteroscedasticity and autocorrelation can be an issue. So this is why we run the fixed effects model one more time, not for its sake, rather for some other finding, and that is for the heteroscedasticity test. xtscc is that command, and the results are showing that there is heteroscedasticity because the statistical significance is there, and it means that this null hypothesis of homoscedasticity is rejected. So one thing is noted, that we are facing the situation of heteroscedasticity. Now we come towards the other thing, that is the test for autocorrelation, and here is the command that I highlighted, and it is also showing statistical significance. It means that the null hypothesis of no first order autocorrelation is also rejected. So it means both heteroscedasticity and autocorrelation, they are present. In this case, the fixed effects model will not be in its most effective form, so we have to come up with some remedy, and Driscoll and Kraay standard error method of the fixed effects model is the solution. So we are going to estimate it, and for that the command is slightly different. In this case we will use xtscc, and then the remaining thing, that is the list of variables, will remain the same, comma space fe, that is the fixed effects, because it is actually a variant, a remedial measure of a fixed effects model. So xtscc is the command keyword for it, and now we press enter, and when we do, we get a regression with Driscoll-Kraay standard error method, and it is based on the fixed effects regression. Here you can see the standard errors are not simple standard errors anymore. They are Driscoll and Kraay standard error method, which is a superior method which overcomes the problem of heteroscedasticity and autocorrelation, which is already found to be existent in this data. So we are now having this result, which is more reliable as compared to the simple fixed effects model. And here you see the justification of using the Driscoll and Kraay standard error method is this, that we now assume that the error structure is heteroscedastic, that is, there is presence of heteroscedasticity and autocorrelation. So then we can apply the Driscoll and Kraay standard error method, because in that case it is more suitable. So this is how we apply the Driscoll and Kraay standard error method approach. And in the next video we'll learn about another variant which is used in panel effects model, that is for the random effects model. Its variant will allow us to get better estimates as compared to the simple random effects model. Thank you.